Good afternoon again. So let's continue our discussion on series loaded resonant. I know I spent a lot of time on SLR, but I'll go faster on PLR because they're similar. So SLR stands for series loaded resonant. What we talked about so far is these waveforms, right? And then the different circuits that goes with with the different time, the different segment of time within one period. So you can see this is the resonant period from here to here, right? That's the resonant period. And there's a switching period. So there are two different frequencies, right? Or two different periods. So that's the resonant period. And here's the switching period, okay? So that's omega naught and that's omega s, right? Or T naught, I should say this is T naught. Resonant period, and here's switching period, right? So two different frequencies. And as you can see, if you want to have DCM, then the resonant two times the resonant period has to be smaller than switching period, right? You can see clearly from this graph. And also one of the things that I forgot to mention is that we already discussed that every single mode here, right? For example, from here to here, anytime any of the devices conducting, like those four, right? The circuit is always resonant, series resonant circuit, right? It's always this kind of circuit, right? And let's call it VX. And VX, as I mentioned last time, that's the combination of plus VD, plus minus VD over 2, and then plus minus V out, right? What I forgot to mention is this right here. During the time when none is conducting, it's not going to be resonant anymore, right? I mentioned that last time, but I forgot to explain what kind of circuit we have there. So when no one is conducting there, when no device is conducting, you're not going to have this resonant circuit anymore, of course, because you can see that's 0 amps, right? And voltage across the cap is just flat. So therefore, the circuit during this time when none is conducting, it's actually going to be looking something like this, right? Because none is conducting, so it's going to be open, and then you have this LC still, and then the output is shorted by the rectifiers. So basically, this type of circuit, right? Because remember, this is a current source, right? So right here is basically, constant current. You have regulated voltage divided by R, by Ohm's law, you're going to get I naught, right? And you have caps right there to maintain the output voltage. So anytime you have output voltage, which you will, you're going to have current, right, by Ohm's law. So when none is conducting over here, right? So therefore, there's no energy being delivered from the source to the load. Therefore, this is going to be open, right? And then it's connected to the source like I drew earlier, like that. And then on the load side, this is going to be a short, right? How? Well, because this current has to freewheel through these diodes, right? So it's freewheeling through this diode, as well as through these two diodes, like that. So it freewheels that way. That's why you need this diode. You need these bridge rectifiers. If you don't have that, then output voltage is not going to be maintained, right? And you get 0 volts. So that's what happens during the time when none is conducting. Okay, that the current, right? Because we have voltage maintained by the capacitor, and across it you have resistor. Therefore, there's going to be current. So that current flows through or freewheels through these 4 diodes. Okay. Making it a short across B and B prime, right there. Does that make sense? Hopefully. So that's the look of the circuit. That's the state of the circuit when none is conducting. Any question on this?
I had a quick question.
Yep.
The output rectifier is what it doing allowing current conduction, so the resonant circuit itself is able to continue to resonate even when the input is turned off? Is that what you're saying?
No, it's not resonating, right? Because it's open. So it's not resonating. You can tell from the current right there is flat. You can tell from the voltage there is flat as well. So it's not resonating, right? But we want to maintain the current. We want to maintain the voltage basically on the output, right? So yeah, so you have, oops, sorry, I should go to the other. So you have this cap that would maintain the voltage even if it doesn't receive energy from the source. And that's when this capacitor discharges, right? Maintaining its voltage. And as long as you have voltage across the cap, then you're going to have voltage across this resistor, right?
Well, that makes sense.
Right. Then you have current. So where does that current flow? Well, it's going to flow through this as well, right? It's going to discharge the cap as well as, you know, freewheels through this, because this is a short basically, right? So some of the currents will also flow through the diodes. Okay, does that answer your question?
Yeah, thank you.
All right. Okay, let's go back to our discussion last time. We stopped at the zero voltage switching, I believe, right? Let's go to that part first. I want you to be able to determine this right here. I want you to be able to, you know, fill up the table. If imagine if these are all blanks, right? There is no yes, no here. I want you to be able to determine why this is a yes, that's a no, and so on and so forth. So let's do that. Let's go back to these waveforms. Where's the waveform? There. So on DCM, that's what we did, right? Still DCM. We did, what did we do? We did the zero current switching last time, right? Any question on this first one, the one that we did last time? All right, so current is actually easier to determine than voltage. Voltage is a bit trickier. So that's why I did zero current switching first at turn on. Let's do the other zero current. And at this time, let's do the turn off. Okay, so let's say if you have, let's see if you have zero current switching at turn off. Okay, so let's look at this waveform. Again, we're still doing the DCM at turn off, right? So we only focusing on the switch, not the diode. Okay? So an example will be this one right there. That's the point when T plus stops conducting. You agree? So that's the time when I turn off T plus, or that's the time when T plus turns off. So let's say we have zero current switching at turn off. And how do we define zero current switching? Remember T0 minus and T0 plus, right? So you look at I across the switch, T plus, at T0 minus, right? What is that current? And then I at of T plus at T0 plus, and see what that current is, right? And if both of the values are zero, then when you have zero current switching. If one of them is not, then it is not zero current switching. So let's take a look. All right, so the easiest one would be T0 plus, right? Because we are turning off the switch. So obviously, after you turn the switch off, it will be 0 amps, right? So right up, this is our T0, right? What happens with the current through the switch after we turn it off? What happens at T0 plus? Well, most definitely going to be 0, right? Because it stops conducting. So that's the easy part, right? You agree with that? Let me see if you disagree. Right? And then what happens at T0 minus? Let's see if it's 0. Well, let me erase this. Again, that's our T0 minus, right? Sorry, that's our T0. Now, what does T0 minus mean again? It means you're going to look at switch current, which is in this case the same as IL, right? Because they're in series. So IL is equal to IT plus at this point, right? They're in series. So if you are looking at if you look at the switch current, right? This waveform right there, and then as the time approaches T0 from the left, if you zoom in, you know, imagine if you zoom in there, like what are you gonna have there if you zoom in? Well, oops. If you zoom in, then you're gonna see, right, current gradually goes to 0, right? This is current through T plus. Gradually goes to 0. And this is your P naught right there. And this is time, of course. And right before T naught, that's our T naught minus. You agree? Since it's following a sine wave, you can see that current gradually goes to 0. So therefore, at T0 minus, if you again keep zooming in, right before T0, you can see that T0 minus is basically 0, right there. You agree with that? Anybody disagrees with that? So therefore, I know that because it follows a sine wave, right before T0, meaning T0 minus, current is going to be very, very close to 0, right there. Any questions? So now, since both current through the switch at T0 minus is 0, and current through the same switch at T0 plus is 0, because both of them are 0, therefore we have a yes for GCS at turn off. So that should be a yes right there. See, that's a yes. Are there any questions on this? I'm doing this slowly. Again, next time is going to be much faster. Any questions on this? All right. If not, let's do the 0 voltage. That's the trickier one to look at. Okay. Let me erase this. I'm going to need to clear this up first. So 0 voltage at, let's do it at turn off first, because I believe that's easier to see. Hopefully, we'll see. How do you do this quickly? All right, so let me erase this first. So now what we're going to do here is whether or not we have ZVS at turn off. So for ZVS, it's 0 voltage, right? So therefore, I need to look at voltage across the switch, T plus in this case, at T0 minus, and voltage across T plus at T0 plus, right? We need to find out what those voltages are. Again, if both are zeros, then we have 0 voltage switching at turn off, right? So I'm looking at this again, this point, same thing, same point, when the switch is off. All right. What's easy to find here between T0 minus and T0 plus, I would say is T0 minus, right? Because we know that the switch is still conducting. You see that? Right before we turn off the switch is still conducting. It still has current, right? So therefore, I know that at T0 minus, voltage across the switch must be 0 volts, because it's still conducting, right, before it turns off. And it's an ideal switch, right? And current through that switch is practically almost close to 0 before we turn off the switch, right? So therefore, there's a non-zero current, very tiny current through that switch, and therefore the voltage across that switch when it's conducting, since it's ideal, is going to be equal to 0. Any question on that one? Okay, the tricky part is what happens at T0 plus. Okay, what is T0 plus again? Well, T0 plus is the time right after, immediately after we turn off the switch, right? At T0, immediately after T naught. Okay, how do we determine voltage across that switch then? Well, for this one, the way I'm explaining it is this. Take a look at what's conducting right after T plus, right? You see from here that D plus, right, is conducting right after T plus, right? So D plus takes over the current after T plus. You all agree with that? So there's a transfer of current from T plus to D plus. And if D plus is conducting, right, if D plus is on, that means voltage across D plus must be 0 if it's ideal, right? Ideal diode. Let's just assume it's ideal for now. Okay, you agree? You can see from there that D plus is conducting, therefore D plus voltage across D plus is 0. Now, why is that significant to know? Well, because I know that T plus and D plus are connected in what?
Parallel.
Parallel, right? So you have to go back to this circuit to ensure or to determine the voltage across T plus. So you can see from here, since T plus and D plus are in parallel, right? As soon as current goes through D plus, creating a short across D plus, that means voltage across D plus is 0 volt. Well, if voltage across D plus is 0 volt, that means voltage across T plus at the same time is 0 volt as well. You see that? So from there, I can conclude that right after T plus turns off, because D plus is conducting, and it just so happens that D plus is right across T plus, therefore voltage across T plus after it turns off must be equal to 0 as well. In fact, as long as D plus is conducting, voltage across T plus will also be 0. Do you agree with that statement? If anybody disagree, please let me know. Okay, since we have 0 volts at T0 minus, 0 volts at T0 plus, therefore ZVS is a yes there. So let's see, at turn off, it is a yes right there. Okay, any question on this one? Let's do the last one. It's a no. Let's see if it's true. So at turn on, okay? So let's go back to here. Now we're going to look at what happens at turn on. Okay. All right. That's going to be, let's say, I'm going to use T minus. It's going to be the same for T plus. But T minus is easier to look at here because it's in the graph. So that's how I'm going to pick T minus. It's going to be symmetrical to T plus. So right here is T minus, right? When it turns on. You agree? That's our T naught. When T minus is turned on. Okay, right there. Okay, let's see what happens after first, because that's easier, right? What is the voltage across T minus after it turns on? Well, it's going to be 0 because it's an ideal switch. Whenever it is conducting current, its current is going to be, so its voltage is going to be 0. So I know for sure that T0 plus is going to be 0 volt. That's the easy part, right? Anybody disagrees with that? Okay, if not, okay, what happens before we turn on T minus? So notice that before I turn on either T minus or T plus, there's always this discontinuous part, right? And as you already know, during this discontinuous part or zero amp segment, you can see that none is conducting. That's the same way with T plus when it turns on, right? See that? When T plus turns on, before it turns on, none is conducting, right? So none is conducting. That's why I said earlier they're the same, right? So that's let's take a look at voltage across T minus when none is conducting. So imagine right here, or you don't need to imagine. I think you can just look at the circuit right here, right? So let's say that none of these devices, right, T plus, D minus, T minus are all not conducting. No current at all, right? So what's going to happen with the voltage across T minus? If there is exactly, if it's not conducting, then there are probably several ways to determine this, but the easiest one would be to look at this loop right here, right? So you can see from there, hopefully you can see from there that anytime none of the device is conducting, then you're going to have voltage across here as well as across there. And that voltage is VD over 2 by KVL. Same thing over there, VD over 2. Is that a sine wave or a constant? Of course, it's a constant, right? That's a DC voltage across each switch. So if I draw voltage across the switch when none is conducting, oh, let me go to here. All right, where is it? Right there. So let me pull this up a little bit more. Right. So during this time, if I were to draw voltage across voltage across T minus, then it's going to be VD over 2, constant VD over 2. Right. So starting from here, right, and then when you turn on, okay, so after when you turn on the switch, right, the voltage across that T minus is going to drop right away, right, because it's 0 volts. See that at 0 volt after the switch conducts. So it drops from, you know, some high value VD over 2 immediately to go to 0. So what happens if you zoom in to that point at T0 minus? What is the value? Well, it's not going to be like sine wave, right? In sine wave, the voltage gradually goes to 0. Here you have a step. See that? That's a step from VD over 2 goes down to 0 immediately. So therefore, I know that if you zoom in, the value of T0 minus, voltage across T minus at T0 minus must be VD over 2. So here should be VD over 2. Does that make sense to you? Because it's a step, right, from VD over 2, and it has to drop to 0 after it's conducting, after it's turning on. Does that make sense to everybody here?
Professor?
Yeah.
Could you also like look and see if the rest of the circuit at time equals T0 plus, like if it, because like I know inductors behave like opens at like right after, like the step response of an inductor, like it at the very beginning it behaves like an open, and a capacitor behaves like a short. Like, could you kind of look at if you close the switch, would current start flowing immediately, and determine it that way?
Probably you could, but it's probably, I don't know if that's easier or harder. When you first start inductor, it acts like an open, right? So,
like if you go back to the other circuit, on like a, yeah, if you look at like T plus, it's in like the loop, it's in series with the inductor, so you know that if it closes, the current can't start up immediately. So on turn on, it's 0 voltage, but oh wait, never mind. Yeah, it's not easier.
Yeah, I don't know if it's easier or not. I have not looked at it that way. But you know, in addition to knowing whether or not it is 0 voltage, can you determine the voltage across the switch when it's turning on, right? So to me, the numerical value, that's what I meant. To me,
you do two birds with one stone.
Right, exactly. So by looking at, by analyzing the circuit this way, using this KVL, it looks like, to me at least, it's easier to determine, number one, that it is not 0 voltage when it turns on. Number two, I know what exactly that value of the voltage is before it turns on, right? Which is VD.
You can see the kind of how it's multiples of VD over 2, sort of.
Yes.
Oh wait, no, VD minus V. Never mind. Ignore me.
It's a factor of 1/2, right? So it is multiple of VD. In this case, the multiplier is 0.5 because it's a half bridge, right? So yeah. Okay. Hopefully that, I don't know if that answers your question, but yes, it's just a different way of analyzing. You can do it differently. You know, you can try using your way, but see if that's easier for you to do, right? But this is just one way to determine that. Okay.
Yeah, that makes sense. Thank you.
You're welcome. All right. So then going back to here. So because at T0 minus, we have a voltage exactly VD over 2 across the switch. And then after we turn on the switch, obviously it's going to be 0 volts because it's an ideal switch. Therefore, we have a jump, right, from VD/2 drop to 0. So therefore, it's a no for ZVS, right? So should be a no. That's what we have here. Any questions on this? All right. If this is a physical, in-person class, the next discussion, I usually call out, your names and see if you can answer the questions, right? Because I'm going to go fast on the next two, right? As you know, we have CCM1 and CCM2. In addition to DCM, we have CCM1 and CCM2, right? So this is continuous conduction mode for the same circuit, right? And you have the capacitor voltage and you have the inductor current. You can see the discussion, it repeats again, just like the previous discussion, right? It repeats. It's the same kind of discussion, right? You look at resonant capacitor voltage waveform, and then you look at inductor current waveform, and you can see the resonance, right? The sine wave, another sine wave, another sine wave. And in this case, there is no zero segment. Oops, sorry. There is no zero segment. That's why it's continuous conduction mode, right? Notice there's no zero segment there, right? So throughout the entire switching period, right? At least one device is conducting. So there is no 0 amp segment where none of the devices conducting, just like the previous mode, right? So at any given time, there's always one device that is conducting. And look at the circuit. Every single circuit, every single state related to which device is conducting gives you resonance. See? Resonant, resonant, resonant again. That's why you always have sine wave, sine wave, sine wave, different peaks, just like before. All right. So the same kind of analysis, right? I'm not going to go through this in details. And what's important for you is one of the important things that for you to notice that which device is conducting at any given time, right? In steady state. So if you start the analysis from turning on T plus, then just like before, right? Current try to flow negative through T plus, but it cannot, right? So it has to go through D plus following a sine wave. But then as soon as D plus conducts, then that would change the voltage into the tank. Therefore it gives you a different peak, right? And look here, before we allow inductor to discharge itself to 0, before we do that, we turn on the next switch. That's totally different from DCM, right? Remember in DCM, we allow inductor to fully discharge until it goes to 0. Then we wait it, right? And then we turn on the other switch. Here, we don't wait, right? Here we turn on the next switch before inductor finishes its discharging state, right? So you can see we still have current through that inductor, and then we turn on the next switch, which is T minus right there. See that? Okay, and then we have another resonant. Now it's the same peak, the same magnitude as that peak value right there, except it's negative, right? It's symmetrical. And then our mirror image with respect to the x-axis. And then you can see after that, it follows the sine wave, it goes to 0, and then it tries to go positive, and then T minus doesn't facilitate the positive current. So therefore, D minus takes over the one across it, right? And then the cycle continues after that, right there. Okay.
Professor, quick question, real quick. I just want to double check. Is the time that T plus conducts and the max time D plus can conduct to the same? They're both omega. Like it's the same frequency of the waveforms, just different amplitudes?
That's correct. Yeah, so the timing would be symmetrical as well with respect to the beginning of the resonant period, right? You have a portion of resonance period. As you can see, we don't have a full resonant, right? We actually stop the resonant right there. Unlike DCM. In DCM, we allow the resonant, right, to occur. That's full resonant in DCM. But here, it's less than TL. It's less than, not T naught. It's less than the resonant period, as you can tell from there. It's not a full sine wave. And the time when this peak occurs with respect to the beginning of the resonant period, right there, should be the same. If I call that X, right, that should be the same as this X right here, the next resonant period. Is that your question?
Yeah, I was just like wondering kind of like what was the max D plus timing, but then it occurred that you're really only changing the time the switch is on too. Like
Yeah.
until you fire the next switch.
Right. And if you want to know the value, numerical value of this peak, you could, right? By looking at the equations for the current. You look at this circuit, for example, and you derive the equation for the resonant, as we did in the beginning of the chapter. And then you have the equation for IL of T, right? And then that's this segment right here, right? And then you'll find out from here what IL peak is, right? Because this is going to be a sine function.
And the initial conditions are kind of specified from the last operating point when you switch, right?
That's correct. But in this case, if you look at when D plus is conducting, the initial condition is 0, right? Right there. Oops, sorry.
Oh, because it's zero current switching.
Well, I don't know. We'll see later. But if you look at inductor current, when it starts, it's at 0. So initial condition is 0. However, the switch right here, initial condition is not 0. Right?
Oh, the diode sees zero current. Yeah, that's what I was getting.
Right, exactly. So yeah, when you derive the equation for the inductor current, you got to watch out which segment you are looking at, right? If you are looking at the time segment where the switch is conducting, then the initial condition is not 0, as you can see from that picture, right? But if it's the time segment where the diode is conducting, then the initial condition is 0.
That makes sense. That makes sense. Thank you.
You're welcome. Any other questions? All right. So yeah, the key here is that you don't allow resonant period to fully takes place, right? To fully take place, I should say, right? That's less than resonant period, right? So if you do that, then you get CCM1, okay? And there's a specific condition for CCM1, right, in the beginning of the chapter, right? I mentioned it's probably here too, right here. So if the resonant frequency, if the switching frequency is in between the full resonant frequency and half. The half is right there. So let me try again. If the switching frequency is larger than half of the resonant frequency, but then less than the full resonant frequency, then you have CCM1. So anytime the switching frequency is chosen to be in that range, then you get CCM1, right? Any question on that? All right, so then let's do the table again quickly. I'm just going to do it one more time, and then we'll go over, we'll move on to the next topic. Let's see. Let me go to the next CCM. Is that this one? No. Is it this one? It is this one. Okay. All right. First of all, before we do the ZCS and ZVS, looking at this waveform, can I use a thyristor for this one? Semi-controllable switch. Can I still use thyristor for this CCM1 mode? Yes or no?
Wait, what was the thyristor condition again? Like it was.
Yeah, thyristor is semi-controllable switch. You are able to tell the switch when to turn on, but you cannot have the control over when to turn off. It will turn off by itself at 0 amp.
Oh, you can't, right? Or you.
Can you? Or
You could. Oh yeah, because you tell it when to turn on based on when D plus, or where it is while D plus is on, because it's hard for me to put it in words, but I think I get it.
Okay, so it's a yes or it's a no for thyristor?
Yes, you can.
It's a yes, very good. Right, remember thyristor is semi-controllable switch. You are able to tell the switch when to turn on, right here, for example, right there. You can see that I don't wait, right? We don't want to wait until that diode current to go to 0, right? I mean, I could turn on at any time before this diode current goes to 0, right? So for example, if I want to turn on this T minus this thyristor at that point, I could. I'm able to do it, right? Because it's a thyristor. But look, this switch always turns off at 0 right there. So therefore, I don't need to have a signal to turn it off, right? If it's a semi-controllable switch, it will turn off by itself at 0 amps. So you can see the reason why I'm able to use thyristors, because this current, or this not current, but this switch for this mode turns off naturally turns off at 0 amps, right? So therefore, you don't need to force the switch to turn off. It will be turned off by itself because it's seeing 0 amps already before the current is taken over by the diode across it. Okay, hopefully that's clear. Reason why thyristor can still work for this one.
Wait, remind me, can we use it in DCM?
Yes, we could, because the same thing for DCM, right? In DCM, current also goes to 0 before we turn off the switch, right? Oh. You see that right here? See, current goes to 0, and then the switch turns off, right? We're not forcing the current to go to 0. It goes to 0 by itself, and then it turns off because D plus takes over. So we don't need to have a signal. We don't have to send a command for the switch to turn off, right?
Oh, but when you can turn on the switch again, we have VD over 2, so we have a voltage, so it's able to be turned on.
Turning on.
I was having trouble with my simulation too, so that's why I'm wondering.
Yeah, turning on is different, right? Turning on, if you are using thyristor, you could turn on the thyristors at any time you want, right? That's not going to be a problem. You can turn on the thyristor at 0 amps. You can turn it on at however many amps you want. I can turn on right here, but that's not going to be DCM if you do that, right? So turning on is fine, but what you need to focus on is turning off. If the switch turns off when its current is reaching 0 amps, then you could use thyristors, semi-controllable switch.
Otherwise, it would just always be on.
Otherwise, it will always be on.
Because it'll never turn off if that condition's not met.
Yeah, if this current is always positive, then yeah, it will still turn on, right? So for thyristors to turn off, it has to go to 0 amps, right?
Oh, I get you. It has to be greater than omega naught T naught, basically.
Yeah, exactly. Okay. Is that good, or still have questions?
No, that's all good. That makes sense.
Okay.
I'll just bring it to office hours or something just because my circuit's being weird.
Okay, sure. How about diode? For this mode, can I use a slow diode such as PN diode? Or does it have to be a fast diode?
Has to be fast.
Has to be fast, why?
Because you don't have that 0 current buffer that you had before for turn off.
Right, you can see that anytime diode is turned off, it's always turned off before its current goes to 0. So we are forcing the diode to turn off right there, right? You see that? So that means the diode turns off while it's carrying some current. So therefore, it's a step, basically, right? So from carrying certain current, and then has to drop to 0, right? And that drop right there, if it's not fast, let's say if that drop is very slow, right? That's not good, right? This corresponds to the reverse recovery time, of course. You need a fast diode so that when it drops, it will take almost no time, and then it'll do very quick reverse recovery, right? So therefore, for this one, since the condition at which the diode turns off is not 0 amps, therefore, you need a fast diode. It doesn't have to be Schottky, it just have to be a fast recovery diode, right? Not PN though, because PN is the slowest, right? So you learn from E410, there is a fast recovery diode, there's a standard recovery diode, there's a line frequency diode, right? So just pick the faster recovery diode. It doesn't have to be Schottky. The reason why I want to say that, because Schottky, I believe I mentioned that last time, voltage rating of a Schottky diode is very low. I think the one that you can purchase nowadays is around 250 volt reverse voltage, right? And this is typically used for high voltage. So you need to have a fast diode, but if you use Schottkys, then you have to put probably many Schottkys in series, right? Which is probably not a good way, not a wise way to do it. So you can buy a higher voltage diode that has a fast recovery time. So they call it fast recovery diodes. You can Google it. All right. All right. So then let me see. Anything else from here? No. All right. Let's do the table. Don't look at the answer. Okay. I'm going to draw the table here. And let's do it quickly. What is it? ZCS and ZVS, I believe, right? And I believe this is turned on. It doesn't matter. That's turned off. All right, so we're gonna do a yes or a no here, right? Yes is a check mark. No is gonna be a cross like that. Okay. So let's do turn on. Do we have zero current switching at turn on? Look at the
No.
No, yeah.
No.
No. Why not?
Current's not zero.
Yes.
Because if you look at D plus, like it's 0, T minus and T plus.
Right there, yes, you can see that T0 plus is not zero. T0 minus is, but T0 plus is not zero. You can see that's a step right there, right? So therefore, because T0 plus is not equal to 0 amps, therefore it's not zero current switching. Oh, sorry, it's not, come on. It's not zero current switching at turn on. How about at turn off?
Yeah,
Why?
because there's no current.
After, how about before?
And because it's sinusoidal before and
Very
after.
good. Got it. That's it. You got it. It follows a sine wave right there. So if you zoom in from the left, right, before you turn off the switch, right, because it's following a sine wave, it gradually goes to zero. So therefore, T0 minus will be zero. T0 plus has to be zero because it's off already, right, after T0. So therefore, it is a yes for zero current switching. Okay. How about ZVS? Let's do it at turn off first. Is it a yes for turn off for zero voltage switching?
Yes,
Yes. Why?
because when the switch is conducting, you have 0 volts at T, which is T minus, and then the diode's conducting, you have 0 volts also because they're in parallel.
Very good. Not just any diode, but it's the diode across it though, right?
The diode in parallel, yes.
Yeah, right here, see T plus and D plus. Make sure you notice that, right? Right after T plus turns off, D plus is taking over the current. And as we already learned from the previous mode, anytime D plus is conducting, its voltage is zero. So therefore voltage across T plus, which is across it, is also zero. So it's a 0 volts before because it's conducting, and it's a 0 volt after. So therefore at turn off, did I say right? Turn off, yes. At turn off is a yes as well. How about at turn on? Last one.
Yes, same reasoning.
At turn on is a yes, you said, right?
Yeah, except for the only difference is that the diode's on after the switch, but same. The voltage is still 0 across one of those.
There's the point. That's an example of a point when I turn on the switch T minus. You agree? That's our T0 for T minus at turn on. Do we have a yes or a no?
Yes, because D plus is conducting, we got 0 volts, and then when the switch turns on, we could still have 0 because the switch is on.
Do we have a yes or a no?
Yes.
Do we have a yes or a no?
No.
Wait, why is it a no?
Take a look at what conducts before and what conducts after. Be careful. when before I turn on T
Oh,
minus.
the other diode's conducting before.
Yes.
Oh, that's why you said it matters which. Oh, I see. I see.
Yes. So if I go back to this circuit right here, right? What happens is that before I turn on T minus, which one conducts? Before I turn on T minus, which one is conducting? Look, before I turn on T minus right there, which one, which device conducting? D plus, isn't it? Yes? Right? So if D plus is conducting, right here, if D plus is conducting, oops, right there, it's a short, right? That means voltage across T plus is what?
VD over 2.
No, across
Oh, wait. Oh,
0.
zero, right?
Oh,
Because,
so the other one has to be VD.
so therefore, before, remember which device is conducting before T minus is turned on is D plus, that guy right there, right? So therefore, when D plus is conducting, its voltage is 0 volts. So therefore, voltage across T plus is 0 volts. If that is the case, if you agree with that, that means there's a voltage across here before we turn on T minus. What is that voltage equal to?
that one is. Oh, VD.
Yes, VD. So now you know that because prior to turning on T minus, the other diode that is not in parallel to it, the other diode, right, D plus is conducting. Therefore, voltage across T plus will be 0. If voltage across T plus, which is across D plus, right, is equal to 0, that means T minus will have to have VD across it. So V0, V of T minus at T0 minus must be equal to VD. VT minus at T0 plus, that's easy, that's going to be 0 because it's conducting already, right? So do you agree with that? Yes or no? Anybody disagrees with that?
Yeah.
Okay, so therefore, do we have a yes or a no here?
A no.
A no, right? It's a no. So therefore, that's a no right there. So you can see the disadvantage of using this mode, right? You have switching loss at turn on, but no switching loss at turn off. That's a trade-off, right? What is the good thing about having CCM1? Take a look at the quality of the waveforms. Which one would you rather have? This waveform right there, or remember, shape determines noise, right? Harmonics. Look at the current waveforms here. Sorry, there's so many stuff going on here. We have the waveform there versus waveform here. Which one is more sinusoidal? CCM1, right? This is more sine wave than this. You agree? Yes?
Could you use a snubber if you're operating a circuit in DCM?
Snub is only for spike. It's not gonna help with the shape.
But
right?
you could make it not break switches, basically, and still use DCM.
Oh yeah. But I don't think that's related to what I'm asking though, right? Because what I'm asking is that if you look at the quality of the waveforms, you can see that this is more sine wave than this.
I was just wondering if you could have like good harmonics while still like with a high power circuit, or if you would need to sacrifice harmonics to operate in CCM.
Yeah, so if your priority in the design is harmonics, then definitely you don't want to use DCM. But that's going to be a lot of noise, right? Especially with the 0 segment right there. That's going to add harmonics. Here, there's no 0 segment, so your harmonics is going to be less here. Right? It's visually it's more sine wave too, right? So the closer it is to sine wave, the less harmonics you get in the system. Does that make sense? Hopefully.
Yeah. And harmonics like are bad, but yeah. So they must be pretty important. Or
yeah, harmonics translates to loss basically. So you have more loss through harmonics. Right? Energy wasted, not energy, but the power wasted for supplying harmonics energy. Right? So you want to have less harmonics if you could. All right. Any questions on this? Any more questions? So the next one is CCM2. I'm not going to go over this, but I would like you to do it yourself. Right? That's the table for CCM1, and here's table for CCM2. So not table, but look at the waveforms for CCM2, and that could be obtained if the switching frequency is larger than the resonant frequency. Right? If the switching frequency that you choose meets this requirement, then you have CCM number 2. And I already showed you I'm showing you the different devices there, right? So T plus, and then D minus, and then T minus, and then D plus. And yeah, look at the quality of the waveform is even better, right? You can see it's looking more like a sine wave now. So imagine the harmonics, the content, harmonic content in this waveform is going to be less harmonics than the previous mode, as well as it's a lot more less than a lot less than DCM. All right, that's kind of the trade-off. And I have the table already for the switching characteristics right here. Or is it right there? So make sure that you try this. Right? If let's say you try this and you don't get the same answer as what I have here, let me know. Right? Or if you're not understanding how I got yes there or how I got no there, let me know. Okay? Or ask during office hours. All right. Any questions on this? Okay, if not, let's look at how do we estimate average output voltage. So please add voltage here. Average output voltage calculation. So we can only estimate. It's not like the previous resonance circuits where we can actually derive the exact equation. For these circuits, we can only estimate. The reason being, you know, if you look back to the circuit right there, right, we have the resonant tank right there, and the input is basically a square wave, right? Because it flips back and forth between plus VD/2 and minus VD/2, right? Depending on which device is conducting. So it's practically a square wave, right? Flipping back and forth between plus VD/2 to minus VD/2 if it's a half bridge. Same thing with the output of the resonant tank. The output also flips back and forth between plus V out and minus V out. Remember that, right? Beginning of the chapter of this circuit. So it's a square wave as well, right? So therefore, it's not that easy to get the exact equation for the average output voltage. So rather than doing that, we can do estimation. How do we do estimation? By using sinusoidal approach. All right, so we're going to assume that this square wave, not assume, but what we're going to do here is that in order to approximate the output voltage, I'm going to look at only the fundamental component of the square wave, right? So fundamental component of this square wave and fundamental component of that square wave as well at the output, okay? We know that this square wave contains multiple components, right? Not just fundamental component, but also number 3, number 5, right? Harmonics number 1, 2, 1, 3, 5, 7, 9, and so on and so forth. So we only look at harmonics number 1, which is the fundamental component. That's it. So that's going to be sine wave, basically, right? Sine wave at fundamental component, fundamental frequency F1, right? That's the same as this frequency right there. Okay. So that's the approximation that we're going to do, sinusoidal approximation. All right. So let's go back here. So the average output voltage can be estimated by using square wave waveform for input output voltage and a sine wave for the tank current, right? So just the first fundamental component, right? Right here, that's why I use subscript 1 right there to signify that we're only looking at the first component in the harmonics of the square wave. Same thing with V, only 1. So VA is the input to the tank, and VB is the output of the tank, right? So you can see I'm only looking at the first fundamental component. Now, I know I'm not expecting you to remember this, but if you have a square wave, right, then Vn, the harmonics, content of this square wave is equal to 4 times V peak divided by pi, right? Or divided by n pi, sorry, n pi. So if it's the first one that we're looking for only, that's going to be V peak, V times voltage peak of the square wave, divided by n is equal to 1. So it's going to be 1 times pi. That's going to be just pi right there, right? So that's why you see this equation right there. Right? I'm looking at only n is equal to 1. So therefore you see 4 times the peak, which is Vd over 2, right? Peak of this square wave, Vd over 2 divided by pi, right? Same thing with the output, right? Output voltage, remember, flips back and forth between plus V out and minus V out. So the peak is V out. That's why you see 4 times V peak, which is V out, divided by pi, because n is equal to 1 again. So again, this is calculated at n equals to 1, as you can see from the subscript right there. So far, so good? All right. So, and then the current that's flowing to the output. Right? If I go back to this circuit right here, right, the current that goes through the output is a rectified version of the inductor current, right? Let me erase this. So you can see that this inductor current right there, right, is going back and forth like a sine wave, right? Back and forth, positive, negative, positive, negative. But when it goes to the output, that current is being rectified. See that by this full bridge. So therefore, if the inductor current goes like a sine wave, output current will be a rectified sine wave like that, right? And that's why right here I put magnitude of current through the inductor, because that represents our output current. Is the rectified value of the inductor current, right? And you learn from EE411. Again, I'm not expecting you to memorize this. If you have a fully rectified sine wave like that, then the average of this, right, if this is the peak value, right, then the average of this current is equal to 2 times the peak value divided by pi, right? And that's what I should have here. Yes, see that? That's why the average value of the rectified sine wave, rectified current, because it's assumed to be sine wave, is equal to 2 times its peak value divided by pi. So if I look for the peak value, solve for peak value, that peak value is equal to I out average times pi over 2. Right? So that's how we set up the model here to approximate the output voltage. Okay, so let me erase this. So now we have a new model of our circuit where we have the same tank right there. Input now is going to be VA1 only, plus minus, and output is going to be VB1 only, plus minus, except now it's a sine wave, right? Not a square wave anymore. This is all sine wave. Okay, and then the load, not the load, sorry, the resistor, this is not the same as the resistor. This is not the same as the resistor that you see here. That's different from that resistor. That's why it's called RE, equivalent resistor. Why? Well, because we change from a square wave to sine wave, right? So it's going to be a different resistor there, equivalent resistor. That could be done. That could be calculated by this ratio, that the equivalent resistor is equal to VB1, right? That's the voltage, divided by the peak of the current, right? IL1 right there, the one that we just derived earlier. So the ratio of the voltage to the current gives you equivalent resistance. And that should give you the equivalent resistance in terms of the actual resistance, the actual load resistance. So that's the actual load resistance right there. Okay. So that should be this. I know I call it differently, but that's the same as R. So this is RL in that equation. Okay. All right. So now I have all the parameters I need. So if I have this circuit right here, right, and here's our output voltage. How do you get the output voltage? How do you get VB1 from the source right here? Well, that's just voltage divider, right? So you can see that this voltage across RE is a fraction of the entire voltage right here, right? So by using voltage divider equation, I know that the output equation, not the output, but BB, I should say, BB is equal to VA times RE divided by the total impedance, right there. And so from there, I get new equations, and then I start plugging in the values for VB1 from the previous equation, right? One of the equation I have earlier. I also changed the values for VA1, so that's your VB1, remember that? VB1, and there's VA1 right here, right? And then the rest of this equation, and afterward you can solve for V out, because that's a V out term right there. You solve for V out from this equation, and you get a new equation for average output voltage equation. Okay, so that's how we derive the equation for average output voltage. But keep in mind that this is an approximation, right? We're not using the square wave, we are using sine wave approximation. All right, and so therefore, because we are using sine wave approximation, which do you think out of the three modes, DCM, CCM1, CCM2, which of the modes do you think is going to give you a closer, a better approximation if you use this equation? Is it for DCM, for CCM1, or CCM2? Which one? Anybody?
Probably CCM1 or CCM2 because they have like a more sinusoidal output.
Very good. I would say CCM2 would be a good, if you use this equation, then the result would be closest to CCM2 than for DCM, right? Because CCM2 is more sine wave than the other ones, right? But again, you can still use this for DCM and for CCM1. It's just going to be, you know, I think, what do you call it? The percent error will be more if you use this for DCM rather than for CCM2. Okay. Any questions on that? And here's the equation for X of L. As you know, that's just reactance of the inductance of resonant inductance, and there's the reactance for resonant capacitance. Okay, so you can use this equation for any mode to approximate the output voltage. Is there another way? Yes, we can use graphical method, just like the previous circuit, right? In this case, since we have resonant circuit, then I could come up with a family of curves that would depend on the Q factor. Remember Q factor, quality factor, right? Depending on how much energy is being stored with how much power is being dissipated. That's the definition of quality factor, right? And I can rewrite the equations, rewrite the previous equation for output voltage in terms of, you know, quality factor and the ratio of omega s to omega naught. You see that? That's what I'm trying to do here. And at the end of the derivation here, I have a new equation that you can also use, right, to approximate output voltage, right? In this case, you can see that the ratio of output voltage to the input voltage is equal to 1/2 times the whole thing right there. But if you look at this equation, there's a Q now in this equation, right? And then if I let Q to be a constant value, right, quality factor to be a constant value, and then vary the ratio, then you have a curve for the ratio of output over input. So if I do that for different value of Q right there, then you get this family of curves right there, starting from Q equals to 1 right there to Q equals to 5, right? So high Q means skinnier, right? As you already learned from, I don't know which class now, 212 maybe. All right. So that's another thing that you can use to approximate the output voltage. Notice that the y-axis is the ratio of the voltages, V out over VD, and the x-axis is the ratio of the frequencies, right? Omega s over omega naught. Okay, so here's an example. I'm not going to go through this in details, but you know, you have all of these values for VD, for CR, LR, right? And giving you a switching frequency and the actual load resistance, and then asking you to determine output voltage. And here I'm using the equation, or no, using the plot, sorry. This one, I'm using the plot. So I found omega naught, right, from L and R, from L and C, and then I found the Q, right, and I found the ratio of Fs over F naught, right? F naught, you get it from omega naught divided by 2 pi. That gives you F naught. And then switching frequency, that's given, isn't it? Yeah, right there. Right, so now you have the ratio of the frequencies. That's going to go on the x-axis of the graph, right? And then you have the Q value right there, which is equal to 1.936. And I do have a MATLAB procedure to do this. So I graph the same equation with Q equals to 1.9, whatever that was. And then here's the graph of the, what do you call it, of the Q curve for V out over VD and V omega S over omega naught. And we are looking specifically for what ratio? 1.17. So 1.17, that's the ratio I'm looking for, right there. So that's 1.17 around that one right there. If I draw a straight line up until it intersects with the curve, the Q curve, and then draw a straight across, line straight across, and approximately is going to be 0.4 for the ratio, right? I give you VD, right? I believe in that equation, in that problem statement. Yeah, I give you VD. So if you get the ratio of VD over V naught, or sorry, V out over VD, V out over VD. Yeah. When you have the ratio of V out over VD to be equal to 0.4, and you know what VD is, then therefore you should be able to get V out, right? Right there. So VD over V out is equal to V out over VD is equal to 0.4. So therefore V out is equal to VD times the ratio from the graph. That's around 40 volts. And maybe I'm using the, yeah, I did. So I also used the other method. I used the equation instead of graph, right? Right here using MATCAD, right? And I wrote the, type in the equation for the output voltage right there without using the graph. Look at what I got, 40.091. Pretty close, right? Not bad. Okay. So graphical method agrees with the equation in this case. All right. Okay. One more thing to finish SLR is this very interesting. I think it's one of the coolest thing about this converter is that if you look at the steady state operating characteristics of series loaded resonance, if you vary the output voltage and look at the output current, you're going to get these curves right here. This is just an example of two different curves, right? Like a family of curves, but only two. And on the x-axis is this, just like the previous graph, is the ratio of the switching frequency to resonant frequency. See that? Omega S over omega dot. From which we know we can determine whether or not we have DCM or CCM, right? So that's the DCM when the ratio is less than 0.5. And we have CCM1 and CCM2 all embedded into this range, right? And so what this plot tells you is this. If let's say that I'm running the converter, right, at output voltage, this is normalized, by the way. This is normalized output voltage, meaning V out divided by V in, right? So let's say that the normalized output voltage is 0.4, and I'm running it at, let's say, 0.75. Oh, no, maybe 0.8. If I draw a line right there, see that? Kind of like that. I assume that's a straight line up. Then you can see that for when voltage is equal to 0.4, right, of the input, you can see it's going to draw around 2 amps, or that this is also normalized. The normalized current is 2. But then if I change the ratio of the, or not the ratio, if I change the output voltage to 0.9, look at the current. Different current, right? There's nothing special about this. Current is different, which makes sense, right? Different output voltage gives you, for the same resistor, gives you different output current, right? So that's nothing special there. But I'm just showing you how to read this curve, okay? So for different ratio of the output voltage to the input voltage, you get different currents. Unless what? Unless you operate this converter with what mode? Can you see that the two graphs merge into a single line? That happens during what? Anybody?
ECM.
ECM. Watch. If you operate, this is really exciting to me, you know. If you operate the converter in DCM, let's say from here to here, right? That's DCM. The two curves merge into one line. What does that mean? That means that it doesn't matter what ratio of the output voltage is, right? Let's say I'm operating it over here. It doesn't matter what the ratio is, 0.4 or 0.9, it will always give me the same what? The same what?
Current.
Current. This is not just any current, this is output current, right? So imagine if I reduce the ratio even more from 0.4 to 0.1, from 0.1 to 0.001, and it will all merge into the same current, the same line, which gives me the same current. Well, what do you call this right here? Ratio of output, and this is normalized. So how do you do normalize? Normalize. I'm just going to do it this way. What do you call this condition? When the ratio of the output voltage to the input voltage is 0.001, let's just say. What do you call that condition? What do you call that? Close to what condition?
Oh, a resistor or?
No, just look at the voltage. Look at output voltage is 0.001 input voltage. Let's say that input voltage is 100. What do you call that condition? Close to? Close to what? How much voltage do you get if the input voltage is 100?
1 volt.
Exactly. Or less than 1 volt, right? So V out is very small, practically zero. What do you call that condition? What do you call V out equal to 0? What do you call this?
A short.
A short, right? So you can see that if I keep reducing the ratio to doesn't matter, 0.00001, it will all merge into the same line, right? So it doesn't matter if the ratio is 0.5, 0.9, 0.00001, it will always give me the same current. Why is that good? Why is that good?
Power quality or?
No. If you don't have these characteristics, what happens if you have just a straight short? What's going to happen with the current?
It flows to infinity, right?
Exactly, yes. But what this does, this is why this is cool, is that this circuit, as long as you are operating it in DCM, then the circuit will give you inherent short circuit protection. So if the output somehow is shorted, current is limited to this current right there if you operate it at 0.3, for example.